In the slide set, link state routing is explained. However, it does not go into details of routing protocols such as open shortest path first or intermediate system to intermediate system, but refers to the basic algorithm for graphs. An important difference is that in the graphs the nodes are the destinations. In reality, you do not want to send packets to the routers as final destination, but via the routers to hosts in networks behind the routers. However, if this was considered, the algorithm representation would become more complicated. The scenario here is therefore a graph where nodes are connected via edges to other nodes. Initially, each node just knows its neighborhood, that is, the nodes that it is directly connected to, and the costs associated to the edges for these connections. Each node broadcasts this information to all other nodes. Consequently, all nodes know after these broadcasts how the complete network looks like. In the following, each node does an internal calculation to determine the best path from itself to all other nodes. Since all nodes have identical knowledge about the network, this leads to consistent and loop-free paths in the network. It is important to note that a node cannot enforce the whole path on its own. A node can only decide to which other node it forwards a packet, but it cannot force the other node to forward the packet it has calculated, because all nodes take routing decisions independently. In the following, we take a look at the Dijkstra algorithm, which is the algorithm inside the nodes. I'm going to explain you the algorithm based on an example. Pseudocode notations are available in the corresponding slide set. Before we start, you have to take note of the color coding that I use for the edges in the graph. A gray edge has not been considered yet, but it will be considered in the future. As you will see, the algorithm considers every edge exactly once. Yellow edges are considered in the current step of the algorithm. Each link may turn out as an improvement to the previously identified path or may not be beneficial. The result that we want to find is the minimum spanning tree, that is, a tree that reaches all nodes using least cost paths. Blue edges are already part of the minimum spanning tree. Black edges have already been considered and are not part of the minimum spanning tree, but such an edge may become part of the minimum spanning tree later. On this slide, the initialization step of the algorithm happens. The algorithm is used to find the minimum spanning tree based on A as its root. At first, we consider the edges which connect A to its neighbors. The costs of the edges are entries into a table that you see on the top. The N is a control column to note all nodes which have already been visited. Currently, A is visited and the other nodes have not been visited yet. In the following columns, D stands for distance to a certain node and P is the path to the node. So here we have costs 2 to reach B, and the node which we use to get to it is A. We find comparable entries for C and D. The nodes E and F are not direct neighbors of A, so that they are unreachable now. This is indicated as infinite costs. In the next step, node D is selected and the link AD is marked as part of the minimum spanning tree. It is impossible to find a better way to reach D than to take the direct link. Maybe this is not obvious to you, but it can be proved by a contradiction. Assume that there is a better way to D which is not the direct link. Then this way has to use either the link AB or AC, but the costs on each of these links are already higher than for the direct AD link, even if D is not reached yet. In the following, the links which are behind D are considered. The link BD does not provide a better way to reach B, so that the entry for B in the table is not changed. The situation is different for the DC link, which provides a path to C with costs 4 if you regard it in context with the AD link. It is important to note that these overall costs of 4 are entered into the table and not 3. This makes sense because we search for the best way to C, and it is not particularly important that the cost on the last link to it is the lowest. Now there is also a way to E with the overall cost too. Please note in the table that we can stop to fill out the column for D because D will not be considered anymore. It is necessary to select another node now, but there are two candidate nodes B and E with overall cost 2. At this point E is chosen by random as the next node. You can make your own thoughts about the consequences of making the selection differently. The two additional links that we consider now provide a better way to C so that the costs are reduced to 3. Furthermore, F has become reachable. In the next step, B is chosen and the link AB becomes part of the minimum spanning tree. The link BC does not provide an improvement. Now C is selected and the link CE becomes part of the minimum spanning tree. The link CF gives a better way to F so that the entry of F is changed. Finally, F is selected and the N now contains all nodes of the network. This is the end of the algorithm. The important result of the algorithm are the edges which are marked in blue. They form the minimum spanning tree, which you can also see on the right-hand side. It is important to note that a node can only send a packet to a direct neighbor. Therefore, you see in the routing table, which can also be called forwarding table, for all destinations the next nodes which have to be used. In reality, these are the routers.